Hey everyone, how are we doing? It is almost exam 3. It's a week from yesterday. It's a week from Tuesday. Today's Tuesday, so it's a week from today, I believe. Double check your syllabus to know when exam 3 is. It's on the syllabus. I always hate saying it because one time I made a mistake and I said the wrong time and that caused issues. Look at the syllabus to see when it is. And of course, you might be watching this in a future semester, so check your syllabus. With that said, we're going to talk about how to prepare for exam 3 for fall 2024. So let's go look at the review sheet. So take a look right here. We are on the review page and we update this semesterly. So whatever semester you're on, you should see related information. And I want to point this out. If we haven't changed anything, you will see review videos down here at the bottom. So very important that you notice that there are videos going over the review test. So if you are like, how in the world do I do testing a proportion? Well, we've got a video for you right here, which walks through all the math, explains how to do it, explains what will give you for the test, explains how to interpret it, goes through the nulls and alternatives, talks through it, and you can listen to what is needed to be learned and understand it via video format. A lot of the videos are shorter than this one. Type 1, type 2 error. We've got good ways to remember this. 5-minute video. So what I want to point out to you here is take your time studying. Don't sit down the day before and say, I'm going to study the whole class. Chunk the material you learn. That's a technique for memorization. So you've got here maybe chapter, let's say 17, which is 2 sample means. So 2 sample t-tests, we go to the chapter review and you go to the 2 sample t-test video. That's chapter 17 right now. I didn't label it by chapters because chapters sometimes change on us, as I've done for my years teaching here. So the 2 sample t-test right here, in this video, these are the concept videos down here at the bottom, concept review videos. I go through and explain to you what is the 2 sample t, when do we use it? So when we use the 2 sample t, here's all the notation for the 2 sample t, how the degrees of freedom works, how the t distribution works. All these things is basically a lecture going over it again, the null and alternative hypothesis for it, writing out the formula, doing an example problem with it, going through entering in the calculations, that's the long part, finding the degrees of freedom for the 2 sample t, and shading the p-value and coming to our conclusion on if we reject or fail to reject the null for the 2 sample t test. So you'll notice right here, these are really good videos to go through, take notes on, make sure you know things like the notation. So as I'm going through right here, we're about to talk about the formula sheet. This is what I ask you. Check out these videos and then write it down. We can only do so much. Every time I teach it, I ask students to write it down. And sometimes I even forget the formulas. And when you have it written down, it's easier to remember it and review it. And also you create a memory when you're writing it down. So don't worry, I've forgotten the formulas before, I've made errors on them, but having a written version that you can look at and also that you've written down is going to help you remember it. So write it down, say it out loud. Those are ways we learn things and it helps us remember it. You've also got the speed run reviews right here where I do a speed run of chapter 17. So this is the same chapter. It's actually the same length as the previous video. It's got an epic intro. Brian Stevens versus chapter 17. Long hair Brian Stevens versus chapter 17. Here it is, chapter 17, comparing independent means. There you go, begin. And you can see all the topics you need to know, going through them, talking about how we compare independent means, showing the standard error formula, showing the degrees of freedom formula, showing the t-interval formula with this is the estimate, this is the margin of error, so I'm breaking it apart via that. Estimate, margin of error, showing the jump output, how to analyze it with the difference between the 2 means. Once again, don't review with me talking right now, but you can see what is reviewed in here, and I'm telling you what these concepts are and labeling them in the jump output so you could find them and do the analysis via jump output so you know what you're analyzing, and you could look at the result via a test right here. So make sure to check this out, check out these videos, go through them, take notes, know what the nulls and alternatives are. Just think of it as a little mini lecture, only 27 minutes of your time, and take notes while watching them. That is my biggest suggestion. Or just put them on in the background if you're just not doing anything. You're like, oh, I'll just put on a video. And then you can just kind of listen to it and maybe take in some knowledge. It doesn't hurt to listen to things again. So with that, we are going to go over the formula sheet now. That's my advice on how to prepare. Start early, take notes, watch the videos, do the practice test. But now let's talk about the formula sheet for exam 3. So the formula sheet, you need to know it, and it's a lot. But it's broken up basically by chapters. So we're going to take a screenshot of this and bring it over here. Let's go ahead and take a screenshot. This thing keeps appearing on the bottom every time I try to take a screenshot. Hide for this document. Thank you. I didn't want that there. Didn't need it. Okay. We're going to bring up Microsoft Word right here. And with Microsoft Word open in just a moment. New Microsoft Word document. Bring it over here. Now you can see the screen again. And let's paste this in. Okay. So closing on all the billion Word documents. So what is there to know on this formula sheet? Let's take a note right here and put in that we are doing one sample T. One sample T is the first thing up here, which is chapter, I believe it right now is chapter 14 or 15. I believe it's chapter 15. It's also got the interval and the test on it, so I think it's 14/15. So if you're looking to review right here, I believe the intervals are going to be chapter 14 and the testing, or this is proportion. Ooh, let me change this. One sample proportion. And that'll be chapter 13. And that'll be chapter 15. Pretty sure this is chapter 13, chapter 15. Chapter 15 is when we start doing hypothesis testing, and chapter 13 was split into two parts years ago, and we've kept confidence intervals and tests on this. But you can see confidence intervals for proportions and tests for proportions, chapter 13, chapter 15, respectively. So let's talk about what all this means. Well, the first thing right here is the estimate of the true proportion, which is the sample proportion. That's also used down here and also used over here. So you have to know what p hat is and how we find p hat. P hat is found via the equation x over n. And think about examples of this that you often can pull from memory. If you talk to 100 people and 20 of them own bunnies, well, then the proportion who own bunnies is this. That's the proportion who own bunnies. It's usually not that nice on the math. You might get something more like you talk to 200 people and 20 own bunnies. X stands for the amount of successes in a sample. So X is the amount of successes in a sample, and N is the sample size, and P hat is the sample proportion. The formula X over N finds the sample proportion. So just keep examples in your head to be like, wait a minute, Brian said, if I talk to 50 students and 20 of them like mushrooms on pizza, then that's 0.40, which is 40%. A sample proportion is basically a percentage. If you change it by timesing by 100. Now, don't do that yet with the formulas. You can at the end when you're interpreting these things, but for the mathematical purposes, you won't be putting in 40% there and 60%. You'll be putting in 0.40, 0.60 if that's what the proportions are, which actually leads to what is Q hat. So we know what P hat is. P hat is the sample proportion, which is an estimate of what the true proportion is. Like you talk to 50 people, 20 of them like mushrooms on pizza. Well, then you would estimate, your best guess is 40% of people like mushrooms on pizza. So think about that. You're like, well, I talked to 50 people, 40% of them like mushrooms on pizza, 20 out of the 50 people. So that's what a sample proportion is, estimate of the true proportion taken from a sample. How do we find Q hat? Well, Q hat, we'll do a slightly different color for this. Q hat is the complicated formula, 1 minus P hat. This means Q hat is the complement, I sarcastically said complicated formula, but Q hat is the complement of P hat. So all you have to do is do 1 minus P hat. So you just say 1 minus 0.40 is equal to 0.60, and that's what Q hat would be equal to right there. So Q hat is the complement of P hat, and whenever you find it, you can just check by making sure these both add up to 1. So if they both add up to 1, you have found P hat and Q hat respectively, or you've miscalculated by finding the wrong P hat. But they should both add up to 1. They are complements of each other. So we know what P hat, we know what Q hat are. We also know what N is, which is sample size. Whenever you hear sample size being talked about, you will hear in questions things like, and we'll highlight that while we're talking about it. Anytime you hear N, you will hear we talked to this many people. And it will usually say from a sample. It won't say out of the full UT population, that would technically be capital N, not for normally distributed. So capital N is the population size, lowercase n is the sample size, and you'll notice a lot of times we use sample sizes to estimate things because we're doing statistics, which come from samples. So most formulas are going to use lowercase n instead of capital N, and we do use capital N for normally distributed, but just ignore that for the moment. Frankly, the notation of capital N is not even really needed as knowledge for this test. Your formulas are going to involve lowercase n. So lowercase n is the sample size. We talked to 100 students. Brian went out and sampled 50 candy bars. That's a lot of candy bars to eat. But that is going to be your sample size. What do we have next? We have in the formula a z star. So what is a z star? Z star relates to from the normal curve. That's where z-scores come from. The standard normal curves where z-scores come from. And the star is very important. Don't forget that this has a star. The star means relative to a percent confidence. So when someone says, I'm 95% confident, the z star for it is equal to 1.96. When someone says they are 98% confident, the z star is 2.3263. We should just say 2.33 or something. When they say they are 90% confident, the z star is equal to 1.645. And that's because if you were to go to 1.645 right about here, you would shade the middle 90% of the curve. And notice as you go further out on that, you shade more of the curve. Now, we will give you these on the test. We don't expect you to memorize them. You should know that a 95% confidence interval is a z-score of about 2. That's the empirical rule, 68, 95, 99.7. So if we asked for a 68% confidence interval, it would be about 1. So these z-scores relate to how much of the curve you are shading to cover the middle possibilities. So that's what the z-stars are relating to, and the star means you get to pick it based on percent confidence. So now going plus or minus 1 z-star, notice that that is plus or minus, you are covering the middle 68% of possibilities around the estimate. Remember we said the estimate is p hat, so p hat would be here at the center of the curve, and then you're covering the middle 68% of possibilities around it. So the z-star, very important that it has a star, means you pick it based on percent confidence. That z star is not the same thing as this z p hat right there. Be careful. That z p hat is the difference between these numbers standardized. We'll talk more about that in a moment. But z p hat is not z star. That's why they're worded differently. Z star is the z-score you pick based on how confident you want your interval to be. Z p hat is the difference, noted in blue right there, standardized by the standard deviation of p hat. So we just have a few more things to cover for this test, these tests and intervals right here. We have the standard error. The standard error is this full formula. So oftentimes when I write this formula out, I write p hat plus or minus z star, and then p hat times q hat over n square root, because I don't like to write standard error because you have to solve it. You don't do SE times p hat. SE is just the abbreviation of this, or yes, SE p hat. SE is just the quantity called standard error of the sample proportion, and it is equal to this right here. So that's what you put in the formula right there. And we said that p hat is the sample proportion, x over n. Q hat is its complement, 1 minus p hat. And n is the sample size, just how many people did you talk to. So that's got the confidence interval fully explained. Just make sure to plug in your numbers and read a question and know how to input the numbers. You're usually good on that. And next we get down to the hypothesis test. So with the hypothesis test, you have once again here the sample proportion minus the hypothesized proportion. Very important to note that this p naught is what is hypothesized by the researcher, which is not from the data. We don't come up with a hypothesis by looking at the data. We come up with a hypothesis, then collect data to test if our hypothesis is true or if we should reject or fail to reject our hypothesis. If we would retain the null, gotta be very careful with the wording. We never like to say that the null is true. We like to say we reject or fail to reject the null. Continue to believe means fail to reject. So how would P naught be worded in a question? Well, it would say something like, Brian believes that 50% of students love Taco Bell. So you would write P naught equals 0.50. Brian believes that 30% of students are from New York. Notice that is not data-based. It's just a belief. It's a hypothesis. So the null does not have data supporting it or to deny it yet. That's why we run the test to see how far things are away. So then we might find in a sample that only 5% of students are from New York. So in a sample, we observe 5% of students are from New York, and this would lead to the difference between these numbers. So you would take the difference right here, and you'd get negative 0.25. Notice if you subtract these, you get that it's 25% lower than we hypothesized. So you're just basically saying the first thing is what you see in the data and how far is that away from your hypothesis, what you thought would be true. So it's like, man, I thought this would be true, but I saw this instead. And you can think about when you would not reject the null is if you saw what you expected, because then the difference is 0. And you're like, well, I saw exactly what I expected. And so I hypothesized this was true and I saw no difference. That would of course lead to a ZP hat of 0, which is no difference between what you hypothesize and what you saw in the data. So you would not reject the null right there. So now you need to do the standard deviation of P hat. Now you might say, why is this not a standard error? Rock kind of knows.
It doesn't matter.
Rock, it kind of little. This is not really on the test. It's so minute. It's because the null is hypothesized to be true. When we write out the null hypothesis, we write the null is that P equals P naught. And with writing that, we're stating that this is P. And we learned earlier that the standard deviation of P hat is equal to P times Q over N square root. So by substituting in here a naught, well, we assume that P naught is P. So we're basically saying P times Q over N square root. Because if P naught is P, then isn't this formula down here just this formula up here? Because P naught is P. Enough on that. It's called a standard deviation because of that instead of a standard error, because standard errors come from estimates. The estimates are the hats. Those come from samples, where these are assumed to be truth because they are P naught, Q naught, which according to the null. P naught and Q naught are complements of each other. So if we know that P naught is equal to, Brian thinks 30% of students are from New York, well then Q naught is equal to 1 minus P naught, and all you do is you check to see if they add up to 1 to make sure you've done them properly. Noel, good to see you. We're going through the formula sheet step by step and marking in the video. Ask questions if you got it. And you run your test. All you do is plug in your numbers, make sure to note each question correctly, but it's very important to know what these things are, P naught and Q naught. So let's go to the next one, the one sample T. Let's mark it in the notes. Got started a little bit early. Wanted to help out and make sure starting early today. One sample T. These are like mini lectures. Formula sheet. One sample T. But one sample T, the t-test and t-distribution and t-interval, all created by William Gossett, who worked at Guinness Beer. You do kind of need to know that. It can appear on the test. Chapter 14 is the confidence interval, and chapter 15 is the hypothesis test. We're going to go over all the notation here because you should know how to read it in a question. Yeah. Canvas content? You bet. We'll do that next. You got it. So check out Canvas content next, everyone. So once again, let me repeat that. William Gossett, William Seeley Gossett, worked at Guinness Beer around 1890 or so, turn of the century. And he was noticing that the beers, his data wasn't turning out what was expected via the normal. And he said, wait a minute, when you have a small sample size, we might underestimate the true standard deviation of the data because we don't get enough outliers. So I need to make kind of a fudge factor for this distribution. I think he did it in Biometrica. I can't remember. Ronald Fisher and other statisticians were a big part of this. But the things you need to know is this man working at Guinness Beer came up with a really cool new distribution called the T, that if you take the normal and you give it, good morning, Braden, you give it thicker and fatter tails, it's going to be a T distribution. What I like to say about the T distribution is Mr. T flattens it down. Now, what does the T always have? And we got some people here, so I want to get some answers. Every T has with it what's? You can see Mr. T flatten it down in a second. Every T has with it what? Every T has with it degrees of freedom. The degrees of freedom tell you the shape of the t, and there's a formula for the degrees of freedom we'll talk about here in a moment. Notice how with 1 degree of freedom, Mr. T goes, I'll pick the fool, and smashes it down. And then it gets more freedom and it goes back towards the normal, and you actually see that classic 1.96. But with lower degrees of freedom, the T has thicker tails and is more kind of compact in the center. But the T is more smashed down when it has less degrees of freedom. So how in the world do we calculate degrees of freedom to find out the shape of the T? The formula for a 1 sample T. Does anyone know in the chat the formula for the degrees of freedom for the 1 sample T? And I'm repeating something to help you remember. The 1 sample T, which means you have 1 mean. This is the 1 sample T because Mr. T is mean if you're doing drugs. The 1 sample T is n minus 1 degrees of freedom. Great job, Noel, right there. N minus 1 degrees of freedom, easy way to remember it. We could go over the theory behind this, but we'll just keep it simple for Stat 201. So n minus 1 means sample size minus 1. We talked to 60 people, 59 degrees of freedom. We talked to 110 people, 109 degrees of freedom. And so you will need to know this when calculating your T's and your P values. So let's look at the formula to start across the top row. The first thing you see in the formula right here is going to be the Y bar. Y bar stands for sample mean. We don't have you calculate means because, especially with lots of data, it takes lots of time. We, of course, can use JUMP for homework. But the mean of the data, the sample mean of the data, is going to be the average of what we saw in a sample. So Brian talked to 50 students, and they spend on average $10 a week on Chick-fil-A. That would be Y bar equals $10. Now, be very careful. This is not mu. Mu is what we're trying to understand here with this interval. This interval from a sample mean is trying to estimate the true mean. We don't know what the true mean is. We only know from 50 students what they spend on average, but we want to figure out what is the truth for all students. That is what mu is. So the Y bar interval estimates mu, and I should have said for the last one, the P hat interval estimates P, because P hat is the estimate and P is the truth. We don't know what the truth is. We only have an estimate of the truth, which is P hat at the moment. So Y bar is the sample mean, and we are trying to estimate the true mean. And we're trying to do this for 1 mean, so we call it a 1 sample T interval. TDF right there, be very careful. It is T star DF, and we do not multiply it by DF. This is the T related to how confident we want to be, very similar to that normal distribution we just talked about, but this time it's a T, and you'd say this is a T with 60 degrees of freedom, and I want to be 95% confident. Does anyone have a guess for about 5,000 points what the T star for 95% confidence is? So this is the degrees of freedom, tells you the shape of the T. Do you know what the T star for 95% confidence is? You'd be shocked. You could probably guess it. I mean, you might be going to the applet, but you'd be shocked that you could guess it. T star with 60 degrees of freedom for 95% confidence. Well, you put 60 degrees of freedom here, and you get the between interval. Remember, we graphed between, and the answer is 2. Say, why isn't it 1.96? Well, that's the Z which the T will approach. The T will approach the Z as it gets more degrees of freedom. So more degrees of freedom means more normal, less degrees of freedom means less normal, and when you reach 60 degrees of freedom, it's actually super duper close to 2. It's basically 2 down to enough decimals. So it's kind of a fun fact that with 60 degrees of freedom, the T-score is actually basically 2, which we often use for 95% confidence intervals, but a 95% confidence interval is 1.96. And so with this, the T-star represents how much area we are covering on that specific T with that specific degrees of freedom. So you have to know what the degrees of freedom are. They tell you the shape of the T. You have to know the star denotes that we are talking about a confidence level for this distribution and how much area we are covering in the middle of it. Be very careful. A lot of people don't shade the middle, and the confidence interval is the middle 95% covered. So next we have the standard error. The standard error is a metric of uncertainty taken from a sample, metric of variation. I like to call it uncertainty, and it is not SE times Y bar. The formula is right over here in full, and that's why usually when I write this out, I write out the following. I say the sample mean plus or minus the T based on a percent confident with n minus 1 degrees of freedom. Let me erase that. n minus 1. I usually just write the n minus 1 here. It's not times n minus 1. That just tells you the shape. And then you times by s over square root of n. So this is the quantity of the standard error right there, fully written out for you, and you plug in. So we have to know what is s, and we have to know what is n. S is the standard deviation of the data. So we would say something like the standard deviation from the sample of 50 students was $3. So the standard deviation is usually just given to you. I don't know many people calculate it by hand now. N is the sample size. We talked to 50 students, n equals 50. So now we get down to the hypothesis test for the one sample mean. This is when you come up with a hypothesized value of what the students might spend at Chick-fil-A, and then you run a test to see if you reject what you believe or fail to reject, continue to believe what you currently believe. So the first thing we see right here is a TDF, which is not the T star DF. Be very careful because this TDF is the standardized difference. There's the difference and there's it being standardized from what you saw in your data and what you expected to be true. So the sample mean is what you saw. We saw students spend $10. The hypothesis is what you pick beforehand. You hypothesize maybe that students spend $15. So you would find the difference between what students spend, and then you divide by the standard error. I'm just going to pretend I found one. We'll pretend it's 2. And then you get a standardized difference. Then that does not go into this formula up here, because that's a confidence interval formula used to make confidence intervals. So that 2.5 would be the difference standardized, and technically negative 2.5, because it'd be negative 5 over 2. We'll talk about how to calculate the standard error in a second. It's the same formula as before, but realize right now that the sample mean is what you see in the data. I saw students spend $10 on average from a sample of 50 students, and the hypothesized mean is just what the researcher comes up with that they want to test. Is it true that students spend $15? You don't see that in the data. You're just coming up with that. It is a hypothesis you have, and it can be pretty much any value. Like, is it true students spend $20? Well, then you'll notice we're just taking how far these numbers are away and standardizing that difference. Now the difference would be negative 5 standardized because the difference is 10, negative 10 over 2, and there it is right there. So you can just hypothesize any value, and then you find the difference with what you observe in your data. So mu naught, mu stands for true mean, and the naught means hypothesize. So hypothesized true mean. And when you write out your null hypothesis, you write the null states that mu equals mu naught, but of course you would plug in the value of 20 to write the following, that we hypothesize that the true mean is equal to 20. And of course, 20 is mu naught in my example here. I'm just coming up with how it would sound to you in a question. And what you need to do then is you need to take and divide the differences by the standard error. The standard error, once again, being the standard deviation of the data divided by the square root of the sample size. So you simply find how much data was collected. There were 100 students talked to. They, on average, had a difference of $5. And you would then take 5 divided by square root of 100, and you would get 5 over 10. And that would lead to the standard error of y bar being 0.5. I am blocking that. That's what I thought. So you just take from what the problem says and plug in the numbers. So now we get to a little bit more complicated. We now get to the 2 sample t, the 2 sample t. So let's put it in the notes here. And the 2 sample t, about 10 minutes on that one, not bad. Okay, 2 sample t. So why do we call it the 2 sample t? Well, it's the difference between 2 means. It's just wow. So with this, you'll notice in the formula literally has 2 means. And we are looking at, oh, didn't highlight the right one. The difference between the 2 means. So you'll notice right there, it's the difference between 2 means. What are we trying to estimate with this formula? What are we trying to test? We are trying to estimate or test the true difference between the 2 means. So notice we just turned this into parameters from what the sample is. So the interval of y bar 1 minus y bar 2 is trying to estimate the true difference between mean 1 and mean 2. And you have to think of examples with this, like when would you use this? Well, maybe you want to test who's better at basketball, Darren or Brian. So you watch Brian play a bunch of games, and you watch Darren play a bunch of games. So you see the mean for Brian, which we'll call y bar 1. Brian got an average 10 points in the game, and Darren got on average 22 points in the game. So if you notice, the difference right there is negative 12 when you subtract them. Remember, this is not the real difference. This is just an estimate of the difference. 10 minus 22 is equal to negative 12. So wouldn't you say Darren's probably 12 points better? Well, that's a good guess. That's a good estimate because that's what we saw in the data. So this would be the estimate of the truth, and it would also be what we would compare to see if there is no difference. Notice how the hypothesized value over here, we saw it in the previous formulas on the right, usually you pick it and you can technically, but a lot of times we like to test, is there a difference? So the first value over here when we do the test is what you observe, and it's there for both of them. So we'll highlight that. But this is the observed difference, whichever way you put it. That is the observed difference between whatever two groups you're testing. So we saw Darren scores 12 more points than Brian because Brian scored 10, Darren scored 22, that's negative 12. And since it's negative, it's indication the second mean is larger. It's an important note to take that whenever your interval is negative, it is an indication that the second mean is larger because the second mean pulls down the value of the estimate because it's negative, and the first mean increases the value if the first mean is higher. I guess it'd be weird if they were both negative. So I don't know, just try to figure out a way to talk about positive values instead of negative values. And so the first part, let's talk about the interval more in depth and go through each part of it. The first part is the estimate of what the true difference might be. We then get to a margin of error as we have with every interval. Then we have another T star DF. So with the T star DF right here, what you would have is you would have another T distribution, and see if you can do this in the chat. If this T has with it, let's say 40 degrees of freedom, and we want to make a 90% confidence interval, that means we need to shape it with 40 degrees of freedom and shade the middle 90%. So that'd be 90% shaded in the center of it. So 90% would be shaded. And so we're only talking about this right here, this TDF. What would the TDF be? Well, on the test, we'd have to give it to you because we don't expect you to use applets. But you go over here to the applet and you say, I have 40 degrees of freedom, I have 90 confidence, and I'm shading the middle, so it's 1.68. If you remember from way earlier, I said the z-score is 1.6445, but you only approach that as you increase the degrees of freedom. You can see it going towards 1.6445. It will not go past that. It will go to 1.6445. And it's, you see, and it'll be 449 if I go even further decimal places. It's 449, 1.6449. It'll, you just keep doing this right here. I think the applet breaks. Oh, I think it broke right there because one, I just want to see real quick. Let me go to Z, 1.6449. It's very important to me. I know these to like ridiculous, insane decimals. Between, I might show span bar that 1.6. Oh, there, no, it rounds. Okay. Well, it's 1.6449, but then it rounds. Okay, learn something new every day. Another decimal to the 90% confidence roll. Very important. I'm laughing at myself. Okay, so the T for that was 1.68, and it's related to covering the middle 90% of the area on a T-curve shaped by 40 degrees of freedom. You might be asking, how do we get those degrees of freedom? Good news for you, and this is a way to remember it. The degrees of freedom for the two-sample T is a too complicated formula. The degrees of freedom for the two-sample T is a too complicated formula, and that's about the only way we ask it on the test. We do not expect you to solve it. It is a formula right here you're about to see on the screen. It is this formula right here. We say it's too complicated. So the one sample T is n minus 1. The two sample T is too complicated. And the reason we want you to know that is we just want you to know it's a different formula. And if you really had to solve it, it would be either in jump output. So we've asked that, like how would you get the degrees of freedom for the two sample T? You would just look at jump output or something like that. Or you could use applets online to find it. So you can see right here, I'm going to one of the applets where we can find the degrees of freedom for the two sample T. Notice it has standard deviation 1, standard deviation 2, sample size 1, sample size 2. So that's everything in the formula. You enter in the values right here, and then you get 214 degrees of freedom, 211 degrees of freedom. It has ways it works out, but you can guesstimate it times with tricks, but just use applets. It's too complicated. So with this right here, the degrees of freedom once again tell us the shape. It's based on sample size and standard deviations. The 2 sample t's formula is too complicated. The 1 sample t formula is n-1 to tell us the shape of the t distribution which we are using. Last but not least, we have a standard error. The standard error, once again, being a metric of variation within samples and what we would expect between the difference between the means. This is not SE times y bar 1 minus y bar 2. This quantity is the full quantity written out over here. So once again, when I usually write my formulas, I do the following: y bar 1 minus y bar 2. I usually put that in parentheses to section it off because that's the estimate plus or minus the margin of error. T star, meaning we get to pick it with a very complicated degrees of freedom formula. And then we times this by square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And this is the metric of the standard error. Once again, being the standard deviation of group 1, which is I watched Brian play basketball, and he had a standard deviation of 3 in his games. And I watched Brian for 20 games. That would be N120. I watched Darren for 30 games. You can have differing sample sizes, Canvas content hint. So I watched Darren for 30 games, and a standard deviation for Darren's games of 2. He had less variation. And you simply just solve out the formula. Be very careful with your math. And then you create your interval. Let's look at the test down here. It's virtually identical because what you'll notice is, and I wish I could just write, let me make this. We'll bring this back here in a moment. What you'll notice is you keep the standard error for this. The t is not the same value, but the standard error can be used. And then you just take the difference and standardize it. That -0, as The Rock would say, it doesn't matter. -0, so it doesn't matter. It's there because it's the hypothesized difference. It's going to zoom back out on me again. There it goes. It's there because it's the hypothesized difference. So you put what you observe, and then you have what you hypothesize. So this is what we observe, and then the other thing is what we hypothesize. So this is observed, and then this is hypothesized. We hypothesize there's no difference. -0 doesn't do anything to an equation. This t that we get from this is not the same t as the t star. Oh my gosh, what have we done? That was a really bad idea. Maybe we should have. Okay, t. There we go. So that's t right there is not the same thing as the t star, because this TDF is the standardized difference. It is not the same thing. You just take what you observe in Brian's game, y bar 1 minus what you observe in Darren's game, y bar 2. Brian got 10 points, Darren got 22 points. Then you divide by the standard error to get the TDF, which is the standardized difference between the two sample means. And last but not least, we are on the bottom of the formula sheet, understanding what these equations are and what they do. And when we would use them, we get to chapter 19, the chi-squared test of independence. And you even have a hint right here. Let's first note this in the notes. And there's a huge hint on the formula sheet on helping for the test. So with the chi-squared test of independence, here's something you should know. When you write out your null and alternative hypothesis, you simply write out, you'll see this if you do a lot of the assignments, x is independent of y. And the alternative is x is not independent of y. So if you have a question like, is where students live on or off campus related to them owning a pet, the null hypothesis would be, and you would just say, where students live is independent of them owning a pet. Where students live is not independent of them owning a pet. You just put in what the x and y variables are named, and you say they are independent of each other. They're not. So you could say owning a pet is and living on campus are independent. You could do that. I like to put it between them. Just makes more sense. And remember, it's the chi-squared test of independence. So if you look right here on the formula sheet, you can get a hint that you're going to put this independent word and make sure to put the not for the alternative, because they're either independent or not independent. And let's take a moment to think about what that means. If owning a pet is independent of living on or off campus, as The Rock keeps saying today,
It doesn't matter.
wouldn't matter if you live on or off campus. That wouldn't tell you anything about owning a pet. I think owning a pet is not independent of living on or off campus, as in living on or off campus would give us information about someone owning a pet. People who live off campus would be more likely, if we look at pet yes, pet no, and go right here, and we have on or off campus with fake data, on campus, off campus, we might see that more students on campus do not own a pet versus the students off campus have the more likely yes group, like the yes being this up here. More students off campus own a pet, and we think they're not independent of each other. Not independent means related. So that is what the chi-squared test does. It compares the distributions of two categorical variables, which is the count data condition. So the chi-squared test of independence will be two categorical variables. So with this, we have to go in and look at the data and first calculate expected cell counts, which is also a condition. Expected cell counts need to be greater than 5. So you have a hint right here for the conditions, knowing that the chi-squared uses expected cell counts and they need to be greater than 5. So when you get your data, you have what you observe. What you observe in the data is what you see. If we're talking about students living on or off campus, and we have on, off campus, owning a pet, yes, owning a pet, no, then we might see on campus that only 10 students out of 100 own pets. And off campus, we might have that for 200 students, maybe 150 of them own pets out of the 200, so 50 don't own pets. Notice this is what you see, and this is called the observed. Very important for a formula coming up right here. To calculate the expected will be the following formula: row total times column total. So I need to make some column totals over here. There we go. And technically, that is row total. Good, that is row total. And then column total over grand total. So, and actually, I'm going to rewrite this really briefly, really quick. Let me put my yes and no's down here. So there, yes, no, and 160, 140. And this is the column total right here. So now we do the following. We circle this number. Let me do this in a different color. Yeah, it's great. Well, and so that's capital N. I don't love it's called. I call that grand total a lot of times. Good answers, no, well, you're right. So this would give the answer for this cell in the table. So when you redo your table right here, you have to get all the expected counts, and the expected cell counts are going to be the following. We have to do this formula. I basically figured that out. It's not gonna be, it's gonna be 16. I think it's gonna be 16. No, it's not 16. I'm doing wrong math. Is it 53.333? We'll write 53.3. And what's interesting is that makes this one 46.7. I'll tell you how I know that in a second. And that makes the one below it 106.7. And that makes this one to the right of it 93.7. There we go. Who is calling me? Oh, it's my sister. Does that make sense, Noel? And can you figure out the formula for, let's say, this cell right here, or that we already did that one? Since we did that one, could you write out the formula to find this number right here? So you have to think, where is that number? And that number would be right here, and they have to take the values and do the formula we just did. So you notice you basically crisscross them, and then you go and you multiply the values as follows: 140 times 200, and I think we don't do it there. 140 times 200 divided by 300, and there it is right there. Oh, I did wrong math. I see it also on the screen. I did wrong math. I was doing it via a trick. I do see it. If you figured out my trick, good for you. Great job, Braden, right there also. And good practice, good work. The trick is, if you know the totals, these values in the expecteds must add up to it. So the trick is they have to add up to the value in the totals. And the 50 is not used because you're only using row total, column total, grand total. Does that make sense, Noel? The 50 is not used because it's row total times column total over grand total. So the 50 is not used in the formula. So it's 200 times 140 over 300, as Braden, great job right there, has done. And we actually found the one error I made, but you can solve this out sometimes by cheating. Not really cheating, but if you know that the expecteds have to add up to the totals, you can kind of figure it out by forced choice. With that said, what are the degrees of freedom for this? What are the degrees of freedom for this? And you actually have the degrees of freedom formula down here. What are the degrees of freedom for this? How would it work if they wanted us to find the yes off? So to find yes off, it'd be yes, and then it'd be off. So there's the formula. You basically times those numbers. Make this a little smaller. So notice it is 160 times 200 divided by 300, and there it is right there, 106.7 rounded. 106.7. I rounded these decimals right over here. 106.7 rounded. Does that make sense, Noel? You go across the row, you go across the column, and then you divide by the grand total, and you multiply. So I like to circle the numbers a lot of times, and then multiply and divide by the total, and that will get you the answer right there. Row total times column total over grand total. What are the degrees of freedom for this table? Degrees of freedom formula is right here. What are the degrees of freedom? So this is the third time we talked about degrees of freedom. First time was for the 1 sample t, n minus 1. Second time was for the 2 sample t, a too complicated formula that you just look at jump output for. We don't have you memorize it. We use applets for it. 2 sample t, too complicated. And what are the degrees of freedom here? And find it for this table. See if you can get it. It's a good one to see if you know the degrees of freedom for it. So for the degrees of freedom, we have to look at the dimensions of the table, and for Canvas content also. So it is 1. Noel, great job right there. We look at how many rows there are, and there are 2 rows. We look at how many columns there are, and there's 2 columns. The formula looks complicated until you realize you can do it with your hands. You can say this is a 2 by 2, reduced by 1, reduced by 1. 1 times 1 is 1. Does that make sense? Because all you're doing is just subtracting 1 row, 1 column, and multiplying together. Be careful, don't use the totals. A lot of people make a mistake and say that's a 3 by 3. It's not, it's a 2 by 2. You don't use the totals, it's how many levels there are, answers to the questions. So that is a 2 by 2, 1 times 1, because you subtract 1 from each, 1 degree of freedom. And the degrees of freedom tell us the shape of the chi-squared. So let's go ahead and look at the chi-squared applet. And you'll notice the chi-squared is another distribution based on degrees of freedom, which lets us know the shape of the chi-squared. So here we go over here, and you put in new degrees of freedom, and it has a new shape to it. It actually becomes more normal with the center of it being around the degrees of freedom, and especially if you go up to about 100 degrees of, I think it's 100. Standard deviation goes to about, it's about 10 there. Yeah, you can tell, because 95% confident would be, oh, I can't do between, too unfair. Or we could go to 97.5, and it should be, yeah. Well, yeah. It's close to what I thought it'd be. So, just having some of the chi-squared. The degrees of freedom for the chi-squared are rows minus 1 times columns minus 1. And it tells us the shape of the chi-squared distribution we are working with. You won't use the applets on the test. Last but not least, we have the cell chi-squareds. So you have to go through and find each cell chi-squared. This is where the fun really happens, and it's going to take a moment. We'll be done shortly with this. You get these formulas on the test, but if something says find a cell chi-squared, we'll do that in a purple right here. You have to do the following. Observed minus expected squared over expected. So you have to do it for each one of these. For the first cell, you would do observed of 10 minus expected of 53.3 over 53.3. Notice we are taking the observed from here. we're taking the expected from, we are taking the expected from there, and you just square the difference. There's the formula. Noel, thank you. I just want to say, oh, you're welcome. For a dual enrollment credit, but it didn't count. Oh, Braden, that makes my day. Let's throw Braden some huge points. Braden, that's so kind of you. Thank you for taking stats again. I'm glad you had fun. Why not? Last office hours, crazy points. Braden, that really means thank you, Noel, too. You've both been pleasure teaching. Clay, good to see you here, Clay. They're just brightening my day. I got a really nice email from a student about a class I've been self-conscious about. I'm teaching 479, and student was like, they said the class was the high point of their semester. Like, that really made my day. Like that, I'm doing the math right here. I appreciate all nice things people say to me. It's very kind, and we should be kind to each other. 35.2. You gotta do it for each one of these. You have to do it for each one of these. So you would go through and do the next one. You can actually just do, doesn't matter which way you subtract them because you're going to square the difference. And 46. What do you do when you get all the cell chi-squareds? Once you get all the cell chi-squareds, what do you do with all the cell chi-squareds? Observe 150, subtract 106.7, do this, divide by 106.7. What do you do with all the cell chi-squareds? You can see it over there in the corner barely. 17.57. What do you do with all the cell chi-squareds when you find them all? To get the Pearson chi-square test statistic. Yeah. Post it on the Discord too. Post questions on the Discord. Post those questions on the Discord. Observe minus expected squared. Over expected. 20.09. What do you do with all the cell chi-squareds when you find all the cell chi-squareds? Oh god, I can't draw that symbol. 14 years of teaching, I can't draw it. Well, so we're doing this right here at the top. What do you do with all the cell chi-squareds? We've been working all the cell chi-squareds. What do you do with all the cell chi-squareds to get the Pearson chi-squared test statistic? To get the Pearson chi-squared test statistic, it's the what of all the cell chi-squareds. What do you do with all your cell chi-squareds? I'm doing it. Add them. The sum of the cell chi-squareds is the Pearson chi-squared test statistic. If I show you the way this looks, I think you should be able to tell me the p-value. The chi-squared has 1 degree of freedom. We're going to find the p-value using x. So we're not on chi-squared. Chi-squared over here, 1 degree of freedom. So chi-squared is always a right-tailed test because we're looking for differences greater than what we found. What do you think? If I put in 113, which is my chi-squared, what do you think the p-value will be? You can look at the curve, 113 almost on the dot. What do you think the p-value will be? That's not the p-value right there. I haven't put in 113 here. Look at the curve and think about where we're at. We landed at 113, which means I need to put a line on 113 and graph to the right of it. So the p-value is going to be what? The p-value is going to be what? Super duper low. It's going to be, don't worry, points right there. It's because we landed way off the curve. It's going to be 0. And with this right here, let's look at how this looks if we looked at the real data. So remember, here is if people own pets, yes or no. So we're going to go look at the real data right here and look at it in JUMP. It's going to be easier to do that. Why is that up here right there? So let's bring up data in JUMP. And we would go here and we'd have pet. And we'd have yes, yes, no, no. And then we have campus. We have on, off, on, off. And then we have the frequency. Frequency with which data occurs. Yes, on campus is 10. Yes, off campus is going to be 150. Wait, yes, that's off campus. Yes, that's right. No on campus is 90. And no off campus is 50. And now we go to analyze fit y by x. We look at, is a pet explained by being on or off campus? Just being on or off campus explained why someone has a pet. Frequency here, good to go. So if you look at this, it's obvious that people on campus have way more pets. 90% of people on, oh wait, don't have pets, excuse me. 90% of people on campus do not have pets versus off campus, 75% of people have pets. And you can see that right here in the data where 90% of people on campus do not have pets, 90 out of 100. And you can also look at the table down here and see it. We might have done a miscalculation on our, no, 113, it just carried more decimals. Yeah, there it is. And you can see you can get every number we just did by going here and asking it for things like the expecteds. You can just go here and say, give me the expecteds, and here is the expecteds. You can say, what are the cell chi-squareds? There's all the cell chi-squareds we did. And oftentimes you see a table like this, and we ask you to figure out numbers, and we usually blank one out. So huge hint right here. A lot of times on the test, we will take this, and we will ask you to blank. We will ask you to find a number. So what is the formula? This is the last question I'm going to ask on this. What is the formula to find the answer for this value? The missing value, tell me the formula for it. Really good test question here. The missing value on the screen, tell me the formula for it. So you have to think what was blanked out and then write the formula to find that. Really good question. This is how a test looks. Kind of ending here with tests. We did that was almost a chi-squared lecture. Only 20 minutes though. Chi-squared mini lecture. Make sure I save all this. And then we're gonna do Canvas content. Does anyone know how to get the formula for that? That missing value. First off, you have to know what it is. It's a cell chi-squared. Then you go to your formula sheet and you say, what is the formula for a cell chi-squared? And the formula for a cell chi-squared, oh, Braden points in the chat. It is observed minus expected squared over expected. So Braden's doing it right there. You simply plug in the values that Braden says, well, I observe, which is the count, which is what we see. And then we take the expected, which the expected is going to be this right here. Sure, works for the moment. So you plug in the values and Braden's done it. 150 minus 106.7 squared. Make sure the difference is squared, not just that value. And then 106.7 right there. And that will equal the quantity of, when you solve it out, that will equal 17.6. And of course, it'll carry all the decimals for us. Just make sure to punch them all into your calculator while you're doing it and let your calculator do the work. Does that make sense, Braden, on how the test often looks? Is that we oftentimes blank out values and say, find this, and you have to know where to look on the formulas and know how to do them. So really good work. Let's do that Canvas content. Here we go. Really good work. I'm very, very proud. Lots of great. I'm lucky because I know, right? It's like, just give me all questions like that. Just put questions where I just have to find a missing value. Like, here's output. Tell me the missing value. Be like, I got this. I got this. Okay. Log into Canvas. Two-factor dual authentic. I got to dual authenticate. Verify it's me signing in. There we go. My Discord. Did I click Discord on my phone? Oh, what's going on? TN Voice is open through December 4th. We're doing pretty good on it. I clicked it right here. I'll take a look at that. We'll talk about it in class. Try to get more responses going. Let's do the Canvas content. Projects need to be graded. Okay, Canvas content, the last Canvas content. The very, very last Canvas content. What percent are we at? We're doing all right-ish. 479 jumped up. I like that. We're at 63%, which is good. Looks like we're going to get to what we need for level 2 bonus. I think level 2 bonus is 70%. 90% is such a hard thing to do. My asynchronous class is not doing as well. I need to send them reminders. But one class has 479 has 66%. I can show this, I think, right? Let me take a picture. Well, I'll bring it over here. And yeah, so it's looking pretty good. It's hard to get all on the screen. Yeah, we're at 63%. I'll send reminders during class and just do it for all your classes. It really helps us as instructors. Like, I read through all my TN Voice, every single one of them, even the mean ones. I get 1 or 2 mean ones. Hopefully not 3 or 4 mean ones. Hopefully not 5 or 6. There's a few mean ones. There's a few I don't like the things on. I don't like your randomness. Stat tool 1, canvas, content. Number 10. Let's do it. When do we use, what are the 4 conditions for the chi-squared test of independence? What are the 4 conditions for the chi-squared test of independence? Does anyone know in the chat the 4 conditions for the chi-squared test of independence? Condition 1, randomness. Condition 2, 10%. And then you pause. And then you pause, and you got to remember the conditions that relate to this. I got a really great video showing it off a lot right here. Review 3, you can find it right there. What are the conditions? So why are you talking about this during this? You'll find out. It'll be worth it. If you write down here, pause right here on it, and you look, you can see the chi-squared, which has 2 categorical variables, which is actually the count data condition. So literally the count data condition is 2 categorical variables, and that's when you're doing the chi-squared. So random, 10% expected cell count data, you got it, Noel? Yep. So that means, yeah, the chi-squared looks at the association between 2 categorical variables. In the chi-squared test of independence, large values of chi-squared indicate a cause and effect relationship. Now, what do you think about those words, cause and effect? What do you think about those words, cause and effect? Let me see here. What do you think about those words? In stats, we like to say we have evidence of things, or they're bad words. Mubot, we're gonna make Mubot really mad right here. Hopefully he's, yeah, that's a bad word. Thank you, Mubot. Lots of bad words in there. Don't worry about it. But we don't. Oh, Brayden, what are you doing, Brayden? Come on, Brayden. Brayden pulled out. Luckily, you misspelled it. Mubot's going to freak out with you writing that right there. We don't accept the null. We don't prove things. We don't know things. We just have evidence of things, or we fail to find evidence of things. So I can almost say with certainty, I am 99%. You made Mubot really mad in the chat. I am 99% confident that anything that is not a reverse question, like we're being like, we don't say the words cause and effect, true. But anything that it would imply we use cause and effect, or things like accept the null, false. We don't do that here. A contingency table is a component in understanding a chi-squared test of independence. What do you think about a contingency table being a component of the analysis with a chi-squared test of independence? What do you think with a contingency table being a component? What do you think? What do you think of a contingency table being a component of the chi-squared test of independence? Ooh, that's mad. True or false? Contingency tables are a component of the chi-squared test of independence. We'll take a look. Contingency table. Chi-squared test of independence down here. So this one's chi-squared test of independence. So here's a contingency table. That's the table we look at to analyze 2 categorical variables. And the mosaic plot is the visualization of it. So the answer should be what? Is the contingency table a component? The contingency table is the visualization of 2 categorical variables. The mosaic plot is another way to visualize them. Contingency table gives you the numbers. It is definitely true. Yep. Below is jump output for the difference between 2 means. Calculate the test statistic. So really good. We just reviewed this earlier. The test statistic is the whatized. The test statistic is the whatized. So we go back to our sheet, which we did earlier. We pet the sleeping bunny. Oh, he's on the wrong screen. Don't wake the bunny. Don't wake the bunny. I should put that in the class, like pet the bunny. So what do we need to do to get the test statistic? It's this down here we're looking at. What do we need to do to get the test statistic? This seems like a really tough question. There's the answer. To get the test statistic missing the output, we need to do what? What do we need to find? What's this? And what is this? What do we need to do? To get the test statistic, this seems like a really tough question. Seems like it. What do we need to do? Your thoughts? When you see it, it even calls it a T ratio. When you see it, you'll be like, what? What do you think we do? How do we find that test statistic? The test statistic is the T ratio. It is the T. So this value right here is what we want to find. Well, so what we have right here is the top. What is, like, give me a word to describe this. Tell me words for this. What would you call this? Give me words for that. How would, what is that? What is that? What are we analyzing with this test? What are we analyzing? What is that? It says y bar 1 minus y bar 2. So what is that? Surely something in this output relates to it. Well, it's not the ratio yet. The whole thing's the ratio. This top part is the what. That top part is the what. So the whole thing is the ratio. A ratio is comparing two numbers, like 5 over 2, 2.5. 10 over 4, 2.5. So a ratio is comparing two things, a bigger thing versus a smaller thing versus a bigger thing. So in yellow, what do we have? What is that called? Think of the minus. It's the what of those two values. Think of the minus. The minus is a hint. We've found the what between those two values. What does this test analyze? It's two means and their what? The difference. What is this quantity called in blue right there? The quantity in blue, not circled, the quantity in blue is what? The quantity in blue, light blue right there, is called the what? What do we call that quantity in blue? Remember, it's a formula. The full formula for it is square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. It's the standard error. So that's the standard error. So how do I mathematically solve this? How do I mathematically solve this to get the T ratio? Just tell me the math in the chat. Be like, oh, just do this. So we've got it highlighted and we have found the numbers in the output. We found what the difference between the two means is 498. We found what the standard error is. The standard error is 8.05. Remember, this is a quantity you find. It's like, what is the standard error? This is not SE times y bar 1 minus y bar 2. It's not that. Maybe written better, it'd be SE and then sub y bar 1 minus y bar 2. It's a subscript of the standard error. So this is maybe a better way of understanding the way it's written is the standard error. But there is only one difference, y bar. Well, what we have right here, we have the difference y bar 1 minus y bar 2 is the full difference between the two sample means. So we have everything highlighted that we need. So what do? Let's try solving it. We have all the values. I'll show some output right here. So write this down or try to do it right here. Because watch, we'll do another example with some more data. And we'll go to Pokemon data. We'll compare the attacks. I believe so, Noel. You've done it. Great job. Yep. Because watch this. We're going to compare the attacks of legendary Pokemon versus non-legendary Pokemon. And we're going to compare their means using a t-test. And look right here. If we take 41.0075 divided by 3.9286, you get 10.4381. And then we might have not carried enough decimals or jumped doing more calculations in the background we don't see on the last decimals. Does that make sense? All I did was take the difference divided by the standard error, because that's what the formula says. The formula is the difference divided by the standard error. So you have to understand conceptually that this value y bar 1 minus y bar 2 is the difference between the two sample means. The standard error is the quantity of the standard error of the difference, maybe written out better as SE sub y bar 1 minus y bar 2, because it's not standard error times y bar 1 minus y bar 2. It is not multiplying. Remember, we worked a lot on the formula sheet. Please check out the formula sheet part of this video where I talk through this and I explain that this quantity right here is this quantity over here on the right. You have to solve it out. I thought the highlight part was only, oh no, that is the difference. That is the full difference right there between the two means. This is the full difference. So it seems tough until you realize how to use the formula. So it's a good question. Because if you know how to do it, it's super quick. You look at it and you go, oh, 498 divided by 805. We just, oh, and they punch it in wrong and get the wrong answer. And that's what always happens. Just, I'm going to do it wrong. There we go. 2 decimal places. Wow. Now it would lead to a p-value of 0. Which of the following is not a requirement for the 2-sample t-test? Should be nice and easy. A, B, C, or D. Which of the following is not a requirement for the 2-sample t? Make sure to check out the conditions video. It is D. Success failure is for proportions. Great job, Noel. These are definitely a memorization thing because you need to memorize the conditions. Great job, Braden. Also right there. He just hit some points right there. Success failure is for proportions. Nearly normal is for means because Mr. T is mean if you're doing drugs. And independent means is going to be the 2-sample t where each mean is independent of the previous means. It means they do not influence each other. And so we should get 100. We'll do another example of this. I went away from the Canvas content. There we go. Submit. 10 out of 10, 10 out of 10. Let's preview again, see if we get anything new here. The chi-square test of independence. Large values of chi-squared show cause and effect. Nope, can't trick me. The result of a chi-square test of independence concludes color choice is dependent on the kindergartner's gender. So do you think we rejected the null or we did not reject the null? Don't even read these answers. Say reject or not reject in the chat. We have concluded via our test that there is a dependency or relationship between gender and color choice of a child. So did we reject the null or not reject the null? Don't even read these answers. You just got to take in what the problem says first. You got to take it in. We did reject the null. So good answers. The null hypothesis would be that color choice is independent of gender. The alternative could be stated that color choice is dependent on gender. So the null, remember, for chi-squared is always blank and blank are independent. So the null hypothesis would be that the gender of a child and their color choice are independent. The alternative, which we need evidence for, is gender is associated or dependent on a child's gender. So with this right here, what would this tell us? Well, since we rejected the null, we know what? Don't read the answers. I'm trying to hint at it. Since we rejected the null, the what? We would know what? Since we rejected the null, we would know what? We know we rejected the null, so what? Since we did reject the null, we would know what? What would we know about the p-value? Because if we reject the null, then this had to have been true. If we rejected the null, then what had to be true? Low p-value. P-value was lower than alpha. Exactly. P-value lower than alpha. Yep. Contingency table. Yep, that is true. We looked at it earlier. Jump output. Take the difference, standardize it. 498.7 divided by 8.16. There you go right there. That's got it. Good to go. Round 2 decimals. Which of the following is not a way to check the nearly normal? Nearly normal is only for quantitative data. So if you know quantitative data, you can take a look right here and think through it. Now, this is a tricky one. This is very tricky. Is it A, B, C, D, or E? I'm going to draw this out right here while you think it through. This is tricky. I was thinking it said bar chart, but bar chart's not on here. So, can you check the nearly normal by looking at a histogram? Can you check the nearly normal with a Shapiro-Wilk goodness of fit test? Can you check the nearly normal by seeing your degrees of freedom are greater than 10? Can you check it with a normal probability plot? Can you use the central limit theorem? Sure, then I'll draw that and draw this right here. There. Which of these answers is wrong that you can't use? Which of these answers is wrong and you can't use? It's a good tough one. Don't worry about being wrong, just take a guess if you... It is C. Noel, you got it. The answer is C. Great job. So you can look at a histogram and generally get an idea of the shape. It's not the best way to do things, but if you see some heavy skew in it, it's not nearly normal. You can look at the goodness of fit test, which is a test with the null that the distribution is normal. And if the p-value is low, you reject the null and you have evidence the distribution is not normal. You can't just say we have at least 10 degrees of freedom and we're good. That's not what we do. And it kind of alludes to central limit theorem with larger sample sizes for the distribution of the mean being nearly normal. But you can't really just say we have 10 degrees of freedom, we're good, or more than 10. Normal probability plot is a plot that tells us the probability it's normal. Remember, our way of remembering this is to read it backwards. The plot that tells us the probability it's normal. When it follows the linear model, not really linear model, when it follows the quantiles of the normal, it is normal. When it follows the quantile, or we believe it's normal. When it follows the quantiles, or doesn't follow the quantiles, we'd have evidence it's not normal. So sure. The central limit theorem is that the distribution of the mean becomes more normal as the sample size is larger, by which we take for the distribution of the mean. So the answer would be C. We would not, someone's probably put in D, but the answer is C. Can you explain why it would not be B? I was confused between B and C. So what a Shapiro-Wilk goodness of fit test is when you have the distribution of data. We go here to analyze fit y by, or analyze distribution, because that's how we look at quantitative data, univariate, its distribution. We look at attack, and here's how the histogram looks. A little bit of right skew. You can analyze that right skew by actually finding the skewness of it, and it's definitely got positive right skew to it. Monster Man in full action today. Monster Man, we haven't seen you in a while, so we got to do one last drawing of you, Monster Man. Right to the high, left to the low, whatever way the tail goes. Some students have told me, they say, I've finished your class, and I still talk about the Monster Man. Right to the high, left to the low, whatever way the tail goes. This is the positive side, that's the negative side, because the negative numbers will be down there. So it does have positive right skew to the data. So is that nearly normal? Not really. We can make the normal probability plot by going here, normal quantile plot, and really doesn't look too bad. It mostly follows the line. So normal quantile plot is leading us to say mostly normal. You can see the right skew there. I hate that jump does it reverse what I usually see, but it's pushed in that direction, but they do their graphic in a reverse way than what I used to do. So the normal quantile plot, or normal probability plot, is going to show us the mostly normal, slight skew to this. I'm more leaning mostly normal. You can do then what is called the goodness of fit test by going to continuous fit and fitting a normal on top of this. This will actually put a normal on top of it and give it the parameters of what we get from our data, mean of 79, 32, and you can see the normal curve is now imposed on the data. So a normal curve has been fit to this, and you notice it's bulging out in some spots, so we do what is called a goodness of fit test to see how good this fit is. The null hypothesis for the goodness of fit test is that it's a good fit, and the alternative is that it's not a good fit, and probably due to, and Anderson-Darling came up with a test too, also Omnibus test for this, but probably because of the high sample size, we are rejecting it, and we see that there is evidence of non-normality because the null is that the data is normal, small p-values reject the null, evidence of non-normality via the Shapiro-Wilk method for testing this, evidence of non-normality via the Anderson-Darling simulated p-value for testing this, but due to the central limit theorem that the distribution of the mean will become more normal, I would say we're probably good because we're analyzing not this data, but the distribution of the mean. And that's where we talk about the central limit theorem applet. So really the central limit theorem is the saving grace we always have to analyze distributions of means, especially if we have a larger sample size, because if the data has a right skew to it, well, then the distribution of the mean will be more normal, especially for larger sample sizes. So if you take 25 observations from this original data, then the distribution of the mean of these samples of means will be more normal. Truthfully, with this one, since it has light skew, do you remember when we talk about large enough sample size? That's what central limit theorem is. Since we are analyzing the distribution of means of sample size 800, the light skew is going to be fine. Does that make sense, Noel? The large enough n condition deals with central limit theorem. So the central limit theorem states that the distribution of the mean will become more normal and tighter by a factor of the square root of n. So the larger n is, the more normal and tighter the distribution is. So even though this has light skew and fails the other methods, the central limit theorem is kind of your, I guess, your golden ticket or whatever to like do it. But that's got it. I'm going to take a quick break, get ready for class. We started a little bit early. Noel, did you get 100 on the Canvas content? I hope. You don't have to say, but I hope you did. We're going to end a little bit early because I'm going to be preparing for class. It's the last day. A lot of fun. Until then, bye for now. Bye, everybody. Bye.